Hi, this is a design and demo discussion of the HyDFS. The HyDFS is a distributed file system that takes inspiration from both Cassandra and HDFS. So now let's have a look at the files that we'll use for the demo. First, we'll see the test.txt. This is the content of the test.txt. Next, let's have a look at the files that we will use to append to the test.txt. So these are the files that we'll be using to append to the test.txt. We will be using two files from two different machines to append to the test.txt. Specifically speaking, we will use machine 2 and machine 6 to append, and we can see the contents of the append files on the screen. Now we will start the introducer to start the HyDFS cluster, and we'll let all the nodes join the HyDFS cluster. We can see that all the nodes have joined the cluster. Once the nodes have joined the cluster, the group membership protocol ensures that the nodes form a virtual ring, and every node has a complete membership list containing the ring ID and the node name. Now we will add the test.txt to the HyDFS cluster. As we can see, the file has been added and is replicated across 3 nodes. The way the file creation logic goes is, first of all, the program checks if the file already exists in the cluster. If not, it calculates the hash. Based on the hash, it will then find the ring ID of the relevant node and its successor and send the file to those successors. Finally, once it receives a quorum of acts that the file is written on the machines, it displays a success message on the initiator. Now let's look at how appends work. We will launch appends for the various appends that we saw earlier from the machines to the test.txt. The way appends work in HyDFS is appends are finally, when they are merged in a totally ordered fashion. Total ordering in distributed systems means that the ordering of all messages and events, or in this case the files, is in a way that ensures that all the nodes agree on the same order. To ensure this total ordering, each appended file is tagged with a sequence number, which is a tuple of the local sender count and the client ID. The primary and backup replicas receive the appended data of the file and its associated metadata. Now, next, let's have a look at how re-replication works. In order to test out re-replication, we will be killing the primary and the second replica of the files, which in this case is the third node and the 10th node. As we can see, the failure detection protocol has detected the failures, and the HyDFS has re-replicated the files on machines 6 and machine 7. Now let's have a look at how the re-replication works in the background. In order to re-replicate, there is a push gossip that runs in the background that gets triggered every time the membership list or the successors of the current node changes. Whenever there is a change of successors, it checks if it is the primary replica for some of the files, and then it would send these updates to its new successors. In addition to the push gossip that we saw earlier, we also have a pull gossip that runs periodically in the cluster. The pull gossip is run on the secondary and the tertiary replica. The secondary replica asks the primary if it is still the backup for a given file X. In response, the primary replica may reply as a yes, in which case the secondary replica has to do nothing, or the primary replica may reply as a no, which means that the secondary replica is no more a replica for file X, so it deletes the file X from its local repository. Or there's a third condition where the secondary replica does not receive a response from the primary replica in a given timeout because the primary replica was dead. In this case, the secondary replica declares itself as a leader and pushes this update to its successors. Similar to the secondary replica, the tertiary replica also runs a pull gossip and asks the primary replica if it is still the backup for file X. The primary replica and the tertiary replica perform similar actions when the primary replica returns a yes and no. However, when the timeout elapses for the primary replica to reply to the tertiary replica will check the membership list if the secondary replica is still alive. If not, then it declares itself as the leader and pushes this update to its successors. Now let's have a look at how the files are getting merged. We call on the merge and we see that the files have got merged. Now we are getting the file on the local machine. As you can see that there are no additional append files anymore. There's only a single file. Let's have a look at the contents of the merged file, which contains contents of the original file as well as the appends that we showed initially. Now let's have a look at how the merge operation works. When the client triggers a merge, the primary and the replicas of the file merge all the appended files by ordering them on the basis of the sequence number and the client ID, which was stored previously as metadata. Since this tuple is unique, this allows us to merge all the files in parallel with ordering without the need of a sequencer. Thank you for watching this demonstration. You can find the links related to this project in the description below.